Hey guys, I hope y'all are having a good day today. I hope it's a lot warmer there than it is here. We've gotten like 5 inches of snow, and we have more coming tomorrow. So it's been awful. But today we're going to start chapter 11. I'm going to change up the lesson plans a little bit because I don't want to go through this whole chapter the week before and then just have to review the whole chapter again. So we're going to go a little bit slower and do chunks. So the lesson plans are going to look a little bit different than what I sent Coach Reese. So I'm sorry about that, Coach Reese. But yeah, so we're going to today look at the many forms of energy, but today we're going to look specifically at kinetic energy and how you calculate that and how much work was done on the car or on a certain object to increase or decrease the speed or the motion, because kinetic energy is energy in motion. So we're going to look at that today, and then I'm going to give you some practice problems, and you'll finish those, and that'll be it for today. So if you want to follow along with me, not if you want to, sorry. Turn to page 248. And we're going to look at a little bit more in depth at the work energy theorem. So think about like having a job, and when you get paid, the amount of money you have increases, right? Look at figure 11.1a. So it shows that what the money you had before plus the money that you received for getting paid is now equal, or the amount of money you have now is equal to that cash flow, and then also the money you had before. So that's what 11.1a is showing. So the difference in the height of the two bars is the cash flow, and that's equal to the pay that you received while you were working. So look at figure 11b, and it's going to show you what happens when you spend money. This is pretty much common sense stuff, but if we take it from a common sense perspective, we can transfer it into like a kinetic energy example, so that will help. So the bar that represents the amount of money in figure 11b you had before, the bar that represents the amount of money you had before you bought that new CD is higher than the bar that stands the amount remaining because you bought something, so your money's going to decrease. And the difference in that shows the amount that you spent, or the amount of the CD in this case, is what they have. So think about, now in a physics example, think about throwing a ball. In chapter 10, we read that when we exert a constant force, F, on an object through a distance in the direction of the force, you can do an amount of work so it's work equals force times distance. That's basically what they're saying. The work is positive, and the energy of the object increases by an equal amount to W. So then suppose the object is a ball, and you exert a force to throw the ball. Okay, it's baseball and softball season right now, so this is a good example. And you exert a force to throw the ball. As a result of the force you apply, the ball gains an energy of motion that is referred to as kinetic energy. So it's huge that you know that kinetic energy is the energy of motion. This process is going to be shown in 11.2a. You can again use the bar graph to represent the process. This time the height of the bar represents an amount of work or energy, which is measured in, I hope you're saying joules. Yes, joules. The kinetic energy after the work is done is equal to the sum of the initial kinetic energy plus the work done on the ball. Okay, we're going to go over this in a practice problem in a second, so y'all will kind of see how this works a little bit more. Okay, so let's think about, so you're throwing a ball. Let's think about the person who catches the ball, okay? Before hitting your hands or the glove, the ball's moving, so it has that kinetic energy, right? In catching it, you exert a force on the ball in the opposite direction of the motion. So the ball's coming this way, you have your glove here, it catches it. So you exert a force in the opposite direction. Therefore, you're doing negative work on it because you're causing it to stop. So now that the ball isn't moving, it has no kinetic energy. This process and the bar graph that represents it are shown in figure 11.2b. The initial kinetic energy of the ball is positive because kinetic energy is always positive because it's moving, okay? It hasn't stopped, and when it has stopped, there is no kinetic energy. So kinetic energy is always moving, and it's always positive. The work done on the ball is negative, so the bar graph represents the work is below the axis. The final kinetic energy is 0 because the ball has stopped. Again, kinetic energy after the ball has stopped is equal to the sum of the initial kinetic energy and the work done on the ball. Okay? So, thinking about how to calculate kinetic energy, we learned in Chapter 10 that kinetic energy of an object is represented by K equals 1/2 mass times velocity squared. The kinetic energy is also proportional to the object's mass. So like a 7 kilogram shot thrown through the air has much more kinetic energy than like a 150 gram baseball with the same velocity. The kinetic energy of an object is also proportional to the square of the velocity of the object. A car speeding at 30 meters per second has 4 times the kinetic energy of a car moving at 15 meters per second. So kinetic energy, like work, is measured in joules. So you need to know that as well. Kinetic energy is measured in joules. That could be a true or false or just a question on your test. So please make sure you know that. So if you look at table 11.1 on page 250, it shows the kinetic energies of some like typical moving objects. This might be something you have to have in some of your practice problems. Actually, haven't gone over your practice problems yet. So if you need it, just refer to table 11-1, and if you need them for your test, of course, they'll be provided for you. Yeah, so let's look at the example problem on page 250. It says, an 875 kilogram compact car speeds up from 22 to 44 meters per second while passing another car. What were its initial and final energies, and how much work was done on the car to increase its speed? Okay, so first we got to figure out what we're looking for in this whole problem. It says what were its initial and final energies, so we need to find 2 different kinetic energies, right? And how much work is done on the car to increase the speed. So we're looking totally for 3 things here. 2 kinetic energies and the work done to increase the speed. Okay, so we have our mass is 875 kilograms. We have the first velocity. It speeds up from 22, so 22 is our V1, and it speeds up to 44 meters per second, so that's our V2. So to find its initial, we have to use the K equals 1/2 times mv squared equation, and just plug in that first velocity that was there. So it will look like K equals 1/2. The mass is 875 times 22 squared. Okay. And that is equal to 2.12 times 10 to the 5th joules. Okay. So here, when you're finding the initial kinetic energy, you use that first velocity. Okay. All right. Okay, so we've done the first part. The second part says to find the final energy. So to find the final energy, we'll just use the other velocity. Okay, so you have 1/2 times 875 times 44 squared. Always remember to square it. When I was in high school, I would always forget to square it and I'd get it wrong. So make sure you remember to square it. That's very important. Okay, so when you multiply 1/2 times 875 times 44 squared, you get 8.47 times 10 to the 5th joules. Okay, this is the bottom one. Okay. So we got the energies. Now we just need to know the amount of work done to increase the speed, right? Okay, so in order to find work, kind of going back to the bar graph example, the work done is, it's the change in kinetic energy. So if going back to the bar graph, how you had this amount of money and then you were given this amount of money and then you have this total amount, that is the increase is how much money you earned. So this is the same way with work. It's the change in kinetic energy or the difference in kinetic energy. So you do work is K2 minus K1. Okay. And because the car is increasing speed, that means the work is going to be more positive, right? Okay, so you have 8.47. Okay, they're both 10 to the 5th, so you don't really have to worry about the 10 to the 5th. So it's just 8.47 minus 2.12. All right, and that gives you 6.35 times 10 to the 3rd joules. And that's how much work was done to increase the speed. Okay. Yeah, those are pretty simple. You just gotta make sure you know what you're looking for and know the equations, and that's pretty much it. Okay. I was going to go on to something else in the original lesson plans, but today I'm going to let you just work on some practice problems because I really don't want to have to review everything that we went over when we get back from spring break. So we'll just go a little bit slower this week with the chapter. Yeah, I haven't looked at these problems, but we're just going to go ahead and say do 1 through 4 all, because this is a very short, yeah, it's only a 14-minute video. Yeah, so go ahead and do 1 through 4 all, and hopefully that'll take up some of your class time. And if it doesn't fill all of the time, please work on something else or see what Coach Reese would like you to do if he needs help with anything, okay? Y'all have a good day, and I will go over these practice problems with you tomorrow, and then we're going to talk about stored energy, which is potential energy. So do practice problems 1 through 4 on page 251, please. All right, y'all have a good one.